All right. So a few pretty important things about the project. Okay. So first thing, the voltage range for the ADC is 1 volt, not 3.3 volts. So in that case, you can call either DC offset or common mode voltage, doesn't matter. So with the DC voltage sitting in the middle, should be 0.5 volts instead of 1 volt or 1.6 volts as what you design in your circuit. It's not going to affect a lot of things because I made this PCB already. I already submitted to JLC PCB for fabrication. Probably will receive it in a week. And the parts are also ordered. Surface mount components, 1206 packages, manageable for your finger. So eventually, when we receive it, you'll start soldering all these parts on it. And so the only thing that matters is the common mode voltage or DC offset over here, right? So this little voltage divider is designed to provide a 1 volt to lift the AC voltage to 1 volt. But now the whole range is 1 volt, so this wouldn't work. But that doesn't matter because eventually, once you receive the PCB, it has all the pads on it, so it's going to be the same footprint. You just grab a different resistor to form a different voltage divider to form that 0.5 volts instead of 1 volt, which is fine. So eventually, you guys will receive that. You'll receive that PCB board and start soldering all the parts on it, or I also ordered these raw resistors and capacitors you can build on the breadboard, but I prefer PCB, just in case PCB doesn't work, right? So I don't have to refund or tuition. Dr. Lee designed the PCB and didn't work, so don't want to blame us. Okay, I did both. Okay, so eventually one of the options should work. And let's go back to here. A couple things. So first, you can see the ADC module. If you follow the official, not official technical document, I think there's an official example somewhere. No, I posted somewhere, but this one? Not this one. Anyway, somewhere else. Okay, so if you follow that one, it has a GitHub repo, has files in it. It's a project folder. So if you download that project folder, it has all the source code. If you dig into the folders, you can find out the .v files. But also, there's a bit file as well, so you can directly program your IPGA board. So today's goal is to just simply program it first, and then let's load that project file and generate the bitstream by yourself as well, and see if that works. See if it can compile. If it compiles, you know that all of the .v files are working for your Vivado version, and eventually you can put your SPI module into that top folder, and eventually build the connections between the ADC and the SPI, so you can complete the project that way. So today's goal is just to I will show you how to do it. It's really simple. Just grab. I'm going to talk about that later. Okay, just go through this first. So it has. You can tell from this diagram, it has a lot of channels. However, for the Basis 3 board, the digital designer didn't use all of these ADC channels because there are limited number of pins available on the board. So what has been used for that Basis 3 board is only, I think I have it somewhere. Let me find out that tutorial first. Here. So here's an example, right? I can see from this paragraph, only ADC channels 6, 7, 14, 15 are being connected from the chip to the pins. So be clear that the chip is designed and fabricated by Xilinx, which is a company making FPGAs, and the board is made by a company called Digiland. So there are two different companies, and Xilinx was acquired by AMD And Digilent, I think, is a relatively smaller company, just selling all these evaluation boards, including the IPGAs and other sensor modules, including the light sensor you have been using for the SPI tutorial. So whatever ADC channels should be used on the board is determined by Digilent, right? So Digilent, if they want to connect the pins from the IPGA to the pin headers on the board, then they can do it. So only channel 6, 7, 14, 15 are used for the XADC pin headers, and can tell from one side, I think it's at the bottom left corner, and these are ground and VCC pins, and these are 3.3 volts VCC of the VCC power for the entire board. And these are the channels, 1, 2, 3, 4, and these channels are differential channels. So it's inputting differences between these two voltages. So it's basically doing a subtraction, and that subtract, the delta V, is being put into the ADC and getting digitized. So that's how that ADC works. It's taking in differential signal. So the reason they want to do the differential signal input is to reduce the common mode noises, because sometimes what is common mode? Common mode noise. Common mode noise is just you have 2 pins of the input, and from the environment and all these electromagnetic noises or whatever, they will reach these 2 pins at the same time. The noises, because these 2 pins they're equivalent. They're just sitting on the circuit, so whatever noise in the environment will reach these 2 pins at the same time. So that's why they're called common mode, because they are the same voltage, same frequency, and same noise. So by doing a differential design, since your signal is different, they are different of the 2 lines, but the common mode noise are the same. So eventually, if they do a subtraction, the common mode will be subtracted from each other. They become 0 or very close to 0, and that's how you can amplify the difference, which is the signal which carries information. The common mode is just noise. So that's the benefit of using differential input for both amplifiers. Sometimes you can see the difference amplifier, right? I've learned that in analog or circuit 1. Why the difference amplifier is more accurate, because of that. It's doing a subtraction. So it's a similar concept. And you can see there are 1, 2, 3, 4 channels, and usually the bottom channel is the plus input and the minus input. So if you do maybe it's the other way, maybe top is plus and bottom is minus. So it's doing a subtraction from subtracting the bottom signal from the top. So this column is channel 1, channel 2, channel 3, channel 4, and these 4 channels represents 6, 7, 14, and 15 by looking at this pin out here. See, XAP, X81P, that's the channel 1 on the pin header. And you can see this is from ADC 6P. So P is the plus channel, it's a differential input, so P is the plus, and N is minus. Alright, so X81P, X81N, they are connected to ADC 6P, ADC 6N, respectively. And for the channel 2 label on the board, on the header pin there, they are pin 14. They're 14, or ADC is the 14 channel. And then channel 3 is 87P, so 87N. And the last one, the 4th channel, which is connected to ADC channel 15. Okay, it's a P and N, right? So these are the connections, and sometimes you'll see the ADC has another ADC channel which is called VP and VN. If you look at the diagram, probably it's showing that very clearly over here. So the differences between the ADC channels, you can tell these are auxiliary ADC channels from 0 to 15. There are 16 channels. And there's another ADC channel called VP_0 and VN_0. So this channel, this differential input ADC channel, is a dedicated ADC. So these 2 pins are not being used for anything else but ADC input. But for all the other ones from 0 to 15, auxiliary is called auxiliary ADC inputs. So these are being used for both ADC input and also general purpose IOs. You can choose which function you want to use for these pins. But however, for the Digiland, I mean, Xilinx designed FPGA, which has all these ADC pins, dedicated pins, and all these MUX pins. But eventually, the Digiland decided to not using any of the dedicated ADC pins. So VP, so these two pins, VP_0 and V_, they are shorted to ground on your Digiland board, and they are not being used. Okay, but we are, for example, we are using, remember, it's the channel 1 to channel 4, but they represents ADC channel 6, 14, 7, and 15. And these are from these ADC pins. Okay, keep in mind. So we're using 4 out of 16 ADC channels from the available channels from the chip. So these are the pins we're going to use. And here's the ADC module. It's a module existing inside the FPGA chip already, and there's no way that you can write a Verilog file to program an ADC, because ADC is mixed signal circuit, has analog components. It's not pure digital. There's no way that I can synthesize the ADC. So ADC is the hardcore already inside. So what you can do is to program your Verilog to create the MUX circuits or decoder circuits, peripherals on the right or left hand side of it. Take the inputs, latches it, or send it back to the input with the signals. So those are digital circuits. That's the things you can customize. So for from the example, you will be able to tell which pin is shorted to where, and I was looking at the top module. You can see here, that's the top module of the ADC instantiation. It has all these ADCs modules, input and outputs being shorted to different places. Then you can see 100 megahertz clocks being used as a clock input for the ADC. And there's an enable pin. So the timing of the ADC is a little bit confusing. They didn't tell you every single detail about it. And I was trying to find out information online. I was able to find something, but getting to the details is a little bit unnecessary for us. So what we need to know for this ADC is just the input and output. So it's like a black box. We don't really care about what's really happening inside unless we need to, right? But for now, we just need to know when the output becomes available. If the ADC means analog signal continuously being put into the input pin, and there will be a parallel digital output. This is a 12-bit ADC. It's a 12-bit ADC. The output is 16 bits, and the lower 4 bits are not being used. So only the top 12 MSBs are being used as ADC result. And for our SPI, I think so the ADC's data out. So this is 16 bits. This becomes 12. So only 12 here is data. All right. And eventually, I think we simplify this even further. While we are trying to do that, because you think about all the modules we have to use in the project. So we have ADC connect to SPI. The eventual SPI will have to relay the data to UART, and UART send it to your Arduino serial plot to see the waves. So UART is 8 bits in general, even though you can send multiple bytes. But I mean, this could be next step. Now seems like there's a bottleneck over there, it's only 8 bits, right? So if this SPI is taking 12 bits data and you want to send it to UR and then through the USB to the computer to display, you probably need to split it in 2 parts. One is 8 bit, one is 4 bits, and you have treat the 4 bits as an MSB over here. It's just complicating things. So I think what we can do is we can simplify this even further, which is only take 8 bits over here. So we are dropping 4 bits of it. So which means when the analog signal is changing, if it's changing a very small scale, right? This part is being resolved. It's resolving that small changes, and it won't be reflected to your output. So only when it's larger than these 4 bits, is flipping this bit, start flipping this bit, it's showing the difference on the data, which is fine because 12 is really sensitive. It's really very sensitive. We don't really have to get that accurate. So the input, remember, the input becomes your the pulses and it's being amplified. So I think we'll be able to see pretty significant changes to these top 8 bits of the data. Okay. So, but keep in mind that it's ADC is outputting 16 bits, and you're only taking the upper byte, and you use it for SPI. Okay, so the SPI will be 8 bits length. And by looking at all these ports and cables, these are disabled, not being used, and these are the ports. Makes sense. And this one, because I already told you they are short as the ground by the board, so we are not even use it. You can either not talking about it, not including this in over here, or you put it there, it's not being used, which is fine. Okay, and I can tell that ADC's output is over here, the out. Okay, this is the output. Something you need to know, it's more important. And there's an enable pin. And it's the EOC out. So EOC is the end of conversion. So the ADC has an internal circuit. It's sending out a pulse to EOC out. And that one is being, you can see, it has the top module has a wire here. It's called enable. And that enable appears both here and here, right? If you have a wire connecting one side of the wire connecting to one port, another side of the wire connecting to another port, which means they are shorted together. So which means for this block, for this guy, EOC is directly shorted to enable. So directly it draws the wire. So when you write that in your Verilog top, it draws the wire from EOC to here. So whenever it finishes the conversion, it's the end of conversion, it sends a pulse, and that pulse enables it for another conversion. So it's called continuous, it's from the continuous mode. So whenever it finishes, it starts doing another one. So it's very common wiring for using this XADC on the business board. I've seen a couple of examples from different places that do the same thing. So keep in mind the EOC is directly shorted to the enable pin by doing this in your top. Okay, you got to enable for both signals, and these are, one is the input, one is the output. So they are basically shorted to each other. And also there's a ready output, ready. And from the example you can tell whenever ready is 1, right? It's sending, it's looking at these 4 bits from 12 to 15 data output. 12 to 15, what does that mean? 12 to 15, right? So it's upper 4 bits over here. Looking at these 4 bits. Okay? So if this one changes, so these ones, so this is 4 bits, right? 4 bits, yeah, 4 bits. So whenever all these 12 bits over here, right? 12 bits over here, starts counting, right? Counting from 0, 0, 0, 0, all 12 zeros. counting until this one reaches all ones, right? All ones, 12 ones. It carries out and starting carry out to this bit, the lower the LSB of the 4 bits over here, and this counts as a 1, right? So whenever it counts up to 2 to the 12th, count to this number, this one gotta carry out and count by 1. So it's like a counter. It's a 2 to the 12th counter. It's about what's the 2 to the 12th? 496, 4096, right? Yeah, so it counts to like 4096 to carry out. So which means when the ADC value changes to 4096, it counts by 1, right? And then another 4096 is counted by 2, so on and so forth. And it's showing a LED pattern here. It's a 16-bit battery. A 16-bit battery sends the LED array. So you have 16 LEDs, and it's changing from like just one LED turned on and more, right? So the voltage is higher, then it shows more LEDs. It's not really representing the voltage itself. It's just like showing a fact, right? How big that is, quantitatively, not really exactly the voltage itself. You know what I mean? Because eventually, if you download to the board, you'll see when it changes the voltage from the power supply, you'll see the LEDs are like doing this. It's like a volume of the speaker or something, you know. Yeah. But it also has a feature to show. Let me see if I have that code. I don't have that posted. So it has a battery to decimal conversion as a BCD code module. It's directly available from the example. So by using that module, eventually battery values are being converted to decimal values. If it's, for example, 32, right? 32. No, it won't show 32. I mean, the decoder has a way to convert the battery to decimal. So eventually, the voltage range from 0 to 1 volt, because that's what we are going to use from the power supply. So the maximum voltage input will be 1 volt being digitized by the ADC, and the minimum should be very close to 0 volts, and these are decimal values. And you can show the decimal values on the 7-segment display. You got 4 units. Eventually it's showing like 1.000. That's the maximum voltage. If you use a power supply, you change the knob. Eventually when it reaches 1 volt, it should show a 1 volt on the 7-segment display. Okay? So eventually for today's lab, it could be used as a partial work for the project, right? For the XADC's demonstration part. If you get that done, definitely you will receive some partial credit on that. So today's lab, the goal is, I don't have a picture on that. Eventually, you got the basic straight board. You connect your power supply here. Never set it up higher than like 1 volt, right? So do this. I'll show you how to set it up. So channel 1, make channel 1 volt DC. Make sure it's 1 volt DC. So the red terminal should be connected to the top channel. Over here, I showed you a diagram. Okay, so see the red cable connect to the top and black connect to the bottom, and you ground all the other channels, the unused channels, so it's not creating noise. You ground it. The reason that you are using a breadboard is the breadboard has a universal ground, so you plug into this, shorting all the ground to one node, right? You got one. So the ground pin on the board, they are internally shorted to each other, so you don't have to connect both of them. Just connect one of them to ground, so the board will be grounded. And so where's the ground? Huh? Yeah, that's right, from IPGA, from the USB, right? The USB has a common ground with your laptop. So eventually, the IPGA's ground is put to the breadboard, and that ground is sent to all these unused pins, and the unused pins are grounded. Okay, to avoid noises. And this one, keep in mind, it's one of the mode being used. I didn't ground this pin and it worked. I was looking at the different modes for operation. It's a bit confusing, and both of them have the port grounded. But I was trying to use a differential input. You see here that explains the two different modes: bipolar, unipolar. I haven't seen any differences yet. So it's showing that unipolar has the plus terminal can be either positive or negative. But let's consider that later. We don't have to worry about that for now, okay? So for now, what you want to do is don't ground your power supply's ground. Don't ground your power supply's black to the IPGA's ground. Keep in mind, we are doing a differential mode input. So it's amplifying the difference between red and black. So red and black directly into the IPGA's pins. Don't ground your black pin. So which means the ground pin is not shorted to the ground rail of the breadboard. Okay? See, I didn't ground it. Don't ground it. And you should be able to see whenever you're setting up, you see there's a knob on the top right corner of the power supply, right? So the knob, you want to change the cursor, just shift the cursor to the right hand side, which is two digit from the decimal point. So when you are increasing the voltage from the knob, it's increasing like 0.01 volt each time. Don't put on the integer side. 2 volts, boom. It's got fried. So make sure it's on the right hand side. So when you're changing it gradually, you'll be able to see that LEDs are shifting. Pretty fun to watch. And also the voltages at the, you can look at the voltage output from power supply and also look at the 7-cent display. It should show a decimal value of voltage. This should match. So the display on the 7-cent display modules should match the power supply's output. Should be very close. Okay, so you can verify that ADC works, right? ADC works. So after that, you guys need to think about. I don't believe you guys can finish everything today, but just let you guys know if you can finish that demonstration really quick. Take a picture, take a video, whatever you want, put in a report, and you can ask me for a level shifter, and also an Arduino board, so you can start programming the SPI interface. So first, you need a IPGA board, right? IPGA, and you need your SPI. Think about that. So Arduino has its own SPI inside, right? It's designed by Arduino's digital engineers. So that SPI has a transmitter and also receiver inside, but you can customize your SPI in your IPGA. So which one should you use to communicate with Arduino's SPI? Thoughts? Yeah, so Arduino has SPI, right? Yeah. So SPI has a, for example, here's Arduino. So the SPI okay, but hardware wise, you couldn't tell. It's basically just SS, SCK, MISO, and MOSI, right? These are all the pins available on the Arduino. Have your IPGA here. So definitely SS to SS, no problem on that. SCK to SCK, no problem on that. Definitely you need a level shifter in the middle, but I'm not doing that. Okay, this is 5 volts, this is 0.0 volts. Okay. Do we need a both for IPGA? Do I need a both MOSI and MISO for IPGA? So what are the roles of these two boards? So IPGA is a sensor, right? So IPGA is a sensor, it's ADC and a sensor. So it sends data to it, but it doesn't receive anything from Arduino. Does it need to receive anything? No. So it's basically a transmitter, right? It's a transmitter. And do you want to use this as a follower leader? That's the question. Because the leader transmitter, follower transmitter will have two different modules. So the difference is, if the leader transmitter, it carries clock. So this one has to generate clock to drive the Arduino board, right? You're gonna be a follower. Why? Yeah, Arduino is gonna send out clocks. Probably normally you won't be able to control this guy's clock, but depending on the data sheet, right? If you can find out, hey, I know how to control, I can turn on the clock, then that's okay. But I think this guy sent a clock to the follower. I think that makes sense because Arduino's designer, they probably don't know what kind of device is being used, right? So they have to determine the clock frequency, just in case that the sensor itself is more modern and is able to run way faster than Arduino. So this guy won't be able to handle that clock. So it has to be a leader all the time. So this one should be a follower transmitter. So you want to use that follower transmitter module available. And so in that case, it's going to be a follower out, right? So it's S out. Wait, follower out. Yeah, SL, I mean, right? SL, so it's going to be this one, missile. So this is not used, which is fine. You don't have to use it. In that case, you know that everything is built within that IPGA chip. So you need to bring that SPI module into this top and make certain connections. Oh no, this is not definitely, sorry. ADC and SPI are in the same IPGA, but not the Arduino's part. Arduino's external. So you have a level shifter in the middle. Otherwise, it's going to damage the IPGA. So I was looking at, because there are different models, different modes to run your SPI. Remember, there's a CPHA, the phase, and the CPOL, right? Two different modes. So the thing is, we have to know which mode the Arduino is running at. So I was doing some search on that, but I don't think I got a definitive answer about the mode about the Arduino. So these are the two snapshots from the data sheet of the Arduino chip. You can see that they do have different SPI modes, like 0 to 3, which using different cycles to sample it or to set up. And I was looking at it and I found out it might be mode 3 or mode 0. I don't know. So it won't be a very difficult setup. If you set it up as mode 0 and you run it, it doesn't work properly, you can switch to mode 3. So it's a really simple C code in Arduino programming. It's just like a SPI mode or something, and processes like 0, 1, 2, 3. So you can change the mode easily in your SPI code. So I was looking at Taylor's example. I still have it here. Here. So when I was looking at the SPI code, right? So she used the SPI.h, which is the standard header file, the library for SPI, and there are a couple of different functions, and it's trying to set up a clock frequency for SPI. You don't have to worry about that because it's getting synchronized. getting synchronized. So it doesn't matter because no matter how the leader is running the follower, it just runs it, right? It just drives it. So we don't have to really worry about the clock. If the follower can really follow that leader's clock, right? Because the leader defines the clock, defines ICK. So if divided by 32 times, divided by like 16 times, doesn't really matter. And this one is older, step bit older, so it's sending MSB first, we're sending LSB first. And we are doing MSB first. Sending MSB first. Why? Because when you're looking at your Verilog code, it's actually taking MSB first into it and then decreasing your index. It's getting worse. You see this? It's index minus 1. Just taking one data, putting into MSB, and index minus 1, and then receive another bit. So that's why it has to be MSB first in your C code for Arduino, right? All right, and okay, here's a mode, SPI mode. So I think she used a mode 0, and she and it worked for most of the data. But I'm going to show you what the issues are. Okay, and then there's a digital high, I think for setting up that make it ready to start. So when it pulls down, it starts the transmission, and then it begins. So when it begins, you don't even need to handle anything in it because this function does everything inside. It pulls it down, enable it, and all the transmission will get started. Okay? For the loop, it transfer, receive it, why there are 8 different receiving blocks and eventually get the one that works. So it was reported by not just one group, but multiple teams from the course project 2 years ago or last year. So which is when they started receiving the signal, and every 8 times the signal becomes correct for some reason. So you'll receive like 7 incorrect data, and the 8th one will be correct. And it's really consistent error. And it's not just reported by one group, but like at least 2 to 3 of them. So the way they get rid of that is to receive like 7 of them and don't use it. You only report the 8th one set.
This is just a quick question. I guess since they already know that it's correct every 8 times, I wonder if it's like a consistent difference. Like I wonder if it's just like, I don't know.
So I'm also curious about what the issues are, right? So it could be multiple things. First, she set it up at mode 0. Could that be mode 3? So if you try mode 3, probably it will solve the problem. Okay, that's what I told you. Why I told you that if you try mode 0, if it doesn't work, switch it to mode 3 and see if that works. That's one thing you can try. Another thing is, think about that. The ADC is running really fast, right? ADC is running really fast. UR is super slow, 9600 bits per second, and SPI is also very fast. Will there be a bottleneck somewhere? I have to think about the circuits. You can see that it's probably a lot of data points are being dropped. I mean, if you compare the data rate, what's really happening is probably ADC is sending a lot of data, right? ADC is sending a lot of data, and the SPI can probably catch up for most of them. Eventually, UR is probably only picking up these ones and send it out. It's only 9600, and I think she set it up as a even faster rate, but compared to SPI and ADC is super slow. See, even though she set it up at a higher rate, but compared to like a megahertz level, it's still super slow. So would that be a problem? I don't know. I mean, the hardware running behind the scene is not customizable for the Arduino. That's why a lot of high-level programming languages really cannot touch the bottom. So what are being dropped, what are being used, you couldn't really tell. Okay. And you can see the SPI code is really simple. And she added so many different blocks. It's just trying to drop these incorrect data and eventually only use the correct one, the 8th one. And the demonstration, I think, could be a problem at a point, because I think we used 3.3 volts for the ADC and likely didn't damage too many of the boards. So it's actually 1 volt. I don't know if I don't see a voltage divider here. So there's a good chance sometimes it's reaching 3.3 volts. So it's lucky that the transistors being built in the IPGA is able to handle that voltage and not getting damaged. So let's try to not do that. Make sure the input voltage is exactly within the 1 volt range from the sensor. And for today, we can guarantee that because we are using a power supply, right? So we can manage it. So don't follow the connections exactly what they did over here, because it's probably using 3.3. You can see this is the power, right? The red cable is the power, and the 3.3 is being delivered to this power rail, and it's being directly used for the potentiometer. Eventually, if you tune it to the maybe rightmost or leftmost side, eventually you are getting 3.3 volts. So make sure you are not doing that, and also explore the modes for the microcontroller for the Arduino and see which mode you should use. You don't have too many options, right? Just the 4 modes. If this one doesn't work, switch to another one. Eventually, it should one of them should match your SPI code. And okay, so one thing is good to know here. Okay, so the C code on the Arduino, it doesn't really care about the bottom level, right? So it's basically just a function, right? So when the data is getting received, it's doing that transfer. So it's trying to grab whatever data they can grab. And for the forward transmitter, see, it's using the forward transmitter. And interface with the forward transmitter, it has to be put into the same tab. But is there anything getting changed? Okay, so here definitely we need to change the data length to 8 because eventually it's being sent to the UART. So it has to be 8. Anything else? Is there a top module? Oh, here's a little top little Verilog circuit you added to it. So which is the ready output. So the ADC has a ready output. Why we know that is because it's a similar code from the example. It's using the ready output of the ADC as a flag. So when ready is 1, it's a little bit invisible, I'm sorry. Small cannot really zoom in. So when ready is 1, you can just do the same thing. When ready is 1, it's sending that to the LED. Okay? And you can use the same thing for interfacing with the SPI. You can see it's only taking 8 to 15, the upper byte of the 16-bit output of the data. You can see here is the 16 bits for output. Where is it? Here, right? You can see here, the 16-bit, that's the data output for the ADC. And that's a wire That's a wire, and that data is shorted to DO out, which is the pin of the ADC. So on the other side of the data, that wire has 16 bits, but we only use the upper byte of the data wire. So the upper byte of the data wire is the output. It's being sent. It's being sent to the LED. So that's a really quick demonstration. You send it to LED, so you can see the data at the LED, right? And also, that data, that upper byte is also shorted since SPI forward transmitter is getting instantiated in the top module here. And you can see data is shorted to the data input of the SPI code. So you got a byte being put into the input of the SPI, right? And missile is the output, right? Sending out. So you don't have to worry about what's going to happen inside, because that's a module you can directly use. You just need to provide the data at the input, right? That's the strategy of the digital design. So the data is available from the ADC, and just put it here and connect it to the data of the input of the SPI, and that's it. You get a clock connected to the SPI. It's going to directly start clocking everything out, right? So the only thing you need to look at is ready, right? So when ready is on, the flag is on, you send it out. So this one is not being controlled. You see? There's nothing controls this. So this controls the data being sent to the LED. You start looking at the LED, but it's not controlling anything here, because the data out from the ADC is directly shorted to the data of the SPI. Would that be a problem? So the ADC keeps outputting data, right, after a certain cycle. So it's like the byte is getting available, like available, right? Available. So SPI doesn't know the timing, and it's constantly receiving it and put it into the SPI's module. Does that matter? Now let's look at this one. Look at this module. Does it matter? Here's the data, right? The input. So that data input has the ADC's output being available, like available like this, okay? After a certain cycle. And that clock is provided by Arduino. It doesn't matter, right? Because every time, whenever, it doesn't matter how often that's getting updated, but there will be a I'm just thinking if there's any like intermediate converted results at the output. So that's why it's constantly receiving wrong, incorrect numbers, and until a certain number of cycles, it start getting correct data. Have to look into the ADC structure, right? So see if it's outputting intermediate values. Usually it shouldn't. The ADC shouldn't output any intermediate values. It should be always the correct outputs. So I don't think so. So it should be always correct outputs, right? So it doesn't matter. So there will be some data available at the data, the byte, right? And then the SPI is able to taking that in. Okay, so it's changing, sending one by one, sending out one by one. If you can design a structure in the middle, so you know what's happening here? You can see the SPI doesn't have a really stable data at the input. Yeah, that's what I'm thinking. So see ADC has data, right? And that's the forward transmitter is over here, the SPI. So this is directly shorted to it. There's no control. It's crazy. There's no control. If you look at the code, it's assuming the data is stable. Right? It's assuming the data is stable. That's why it's like taking the time, getting the index, decrement by 1 each time, right? And sending that to missile, right? It's the output. As a serial, that's a missile, that's the output. Okay, it's trying to take the time, right? Using that index, right? Index minus 1. So it's basically assuming this is stable, right? And it's like picking up 1 and send it, picking up 1 from MSB to LSB, it's sending 1 by 1. That's not good. Why? Because ADC is running so fast, right? It's running so fast. I think by 100 megahertz, the clock is assuming that the fastest rate it can do is 1 mega samples per second. Sometimes you'll see S. It's a capitalized S. It's 1 mega S per second. Okay, so this means samples. So which means like these ones, the byte here is getting updated every like 1 million times a second. Are we running the same speed? So which means whenever you are taking this bit out and sending it here, and everything here getting updated already. So that is why she's seeing problems.
So it's probably like the speed, I guess, because it's doing everything.
This one?
Yeah. Like.
Let's see.
Because she might.
Oh, that depends on the clock of the Arduino, right? We don't even define the clock in this module. But can we design something within here to get rid of this issue?
It's what we do with that other network latches that like basically save the data.
Yeah, so the thing is, this one keeps sending 1 by 1 to missile, right?
Mm-hmm.
Once it's done, it should flag it, right? It should send a signal here, right? And that signal should be used for this guy to update it. So which means, is there a flag? Busy. So what is busy being used? Busy.
I think it's stops transmitting.
Yeah.
Stops.
Here, right? Oh, busy is 1. When it's transmitting busy. So the transmitting is just sending data. Okay, so it's within that. Only busy becomes 0 when it's getting to stop, right? Whenever it already sent 7 or 8 of the data points. That makes sense, right? It's not busy anymore. So whenever it's sending, busy is 1. And otherwise 0. So when busy is 1, so only update this guy when busy is 0, right? So we'll do it's a Verilog circuit, right? So if busy is 0, you name another register here, data in or whatever. So data in or something to receive data from it, right? Like a latch, D3 file. It's getting latched. Otherwise, this is like a rising edge over here, right? Only when this is 0 to rising edge, so boom. Okay? So we got a set of data which is the complete version. But I think what you said is correct. Probably it's 1/8 of the frequency. That is why you are getting correct value every 8 times. Okay, so something to improve. Okay, I mean the code is already available over here. Most of them are over there. You can directly copy and paste. But just adding this little feature over here to make it correct. See if you can get it functioning.
It's basically a latch, right?
It's a bit of latch, yes. So here's the signal. You already have the signal available.
Yeah.
Here, right?
Oh, cool.
It's a lot of fun.
Yeah.
Okay, so once that is then you can make this correct, and this guy is sending data. So this guy is able to send the data reliably through missile to Arduino. So Arduino will be able to receive a correct data within that cycle, right? It's going to be a correct byte. And the following ones will be easy because that byte is corrected in saved in one register, and you just give it to UART. Even though UART is slow, right? It's just like doing its business. It won't be able to receive a second one immediately, but it will dedicate it to sending that byte it receives, and maybe just ignore the other ones. So like it ignores it has a lot of data coming in, it's in the buffer. If it's not being handled, it will be dropped, even though we don't have the access to the bottom level circuit design of the UART. But eventually the logic probably works in the way that all the ones that are not being taken will be dropped. So it's just, you just lose it, which is fine. I mean, there are so many data points, and it takes that byte, it's gonna, commit it to sending that one and finish it first, and then take another one over here. So after you get a reliable byte over here, I think you'll be fine. Okay? So you don't need that preamplifier in order to get this work. You can keep working on this, maybe verify that, demonstrate that little display first, the easiest one from example, and then start programming this little circuit over here, and place your SPI module into your top and involve this guy over there as well, and make it ready for Arduino interface. So hopefully Thursday, I can give you the Arduino boards and level shifter so you can start testing it. Okay? So it seems like the mode doesn't really matter. Mode 0 to mode 3 doesn't really matter. Right, let's try different ones and see until you see a functioning one.
Are the modes like how it receives the data?
What's that?
Are the modes like how it receives the data, or what are the modes? So there's
The modes are for the
ADC, right? Or for the
no SPI.
oh, this is my bad.
Yeah, so the sequence you can find over here. It defines like when the data is made available to missile and when it's getting latched to the receiver.
Oh, okay.
That's how. So there are 4 different modes.
Cool. That's what it's done.
Yeah. Okay, so for the rest of the lab, let's just get that demonstration work. Before turn on the power supply, let me check your circuit work. So not the pay $80 about